Um, Welcome to Further Solutions Academy. Please do well to share and subscribe on our YouTube channel. And if you have any comments or contributions that you'd like to reach us, please endeavor to reach us at +234 80 95990. So endeavor to reach us on this contact. You can call us, you can send us a WhatsApp message, or you can even reach us via Telegram for any comments or contributions. So this is Further Solutions Academy. Please do well to subscribe to our YouTube channel. Just like we discussed in our last class, we talked about showing the relationship, where we derived an equation showing the relationship between Kc and Kp equilibrium constant. So today, like I said in our last class, we will be experimenting, or we'll be solving some problems. On the relationship between Kc and Kp. So we'll be talking about calculations involving Kc and Kp. This is a sequel of video to the derivations we have done earlier. So please follow me as we continue on this lecture. So let's say we have, for a Haber process, we have the equation nitrogen gas with 3 moles of hydrogen gas to give us 2 moles of ammonia gas, 2 moles of ammonia gas, to give us 2 moles of ammonia gas, and we're giving our Kc to be 9.60 at 300 degrees Celsius. And the question says that we should calculate for Kp at this temperature. Calculate for Kp at this temperature. I would like to divide the board at this point because we'll be having a long calculation. So remember, please make sure you check our last video on equilibrium constant and derivation so that you can understand this better. The relationship that connects Kp and Kc is given as Kp is equals to Kc RT delta N, change in N. So this is the relationship that holds for this kind of equation. So we are using this to solve for the equation. When you see a problem like this or a question like this, you look deeply at the parameters you are given. Sometimes you may need to tweak some parameters, you may need to adjust some parameters to reach the particular solving that you want to do. So now I've been given my Kc. Kc is given. Our R represents our molar gas constant, which is 0.08206 liter atm per mole per Kelvin. So because we are using this value of our R, then definitely our temperature that was given needs to change. So the temperature we are using needs to change. We are giving our temperature in 300 degrees Celsius, so we need to convert it to what? To Kelvin, because of our molar gas constant we are using. So our temperature conversion of this, our T, becomes 300 degrees Celsius plus 273 Kelvin. This gives us 573 Kelvin as our temperature. So R is given, T is given, Kc is given as 9.60, and we are told to calculate for Kp. But remember, delta N is here, so we need to solve for delta N. And like if you check our last video, we're told that delta N is equals to the sum of the moles of the gaseous product, minus the sum of the moles of gaseous reactant. Where delta n was given as C plus D minus A plus B, where C and D are the number of moles of the product and A and B are the number of moles of the reactant. So if we look at our equation, we see that this is the reactant side and this is the product side. So the number of moles of the product, we have just one product, so that becomes 2 minus the reactant. We have 3 plus 1 mole. 1 mole is the coefficient of nitrogen here, so definitely we have 1 mole there, so that becomes 2 minus 4. That is where we have 1 plus 3. Sorry, let me write that clearly. So that is 1 plus 3. That becomes 2 minus 4 is equals to what? Minus 2. I believe this is basic math, so we should not have any problem with that. So we have all the parameters that are needed. Let's just substitute this into our equation. So we have Kp is equals to, our Kc is giving us 9.60, then into brackets our R 0.08206 times our temperature 573 Kelvin raised to power of our delta n, which is minus 2. As a mathematics student, we show that this is a negative sign, so we could rewrite this to be 9.60 over 0.08206 times 573 all squared, if I'm right, according to mathematics. So if we have this and we use our calculator very well, we should be getting an answer of 4.34 times 10 raised to power minus 3. That's 4.34 times 10 raised to power minus 3. There is no unit for this because it is an equilibrium constant. So we are left with this answer. And that is how we have solved this particular problem, showing the relationship between Kc and Kp. Let's solve one more question and see whether we can understand this very well. Let's just solve one more question. A similar question to this. So like I said, let's solve another question. Okay. Let's have this question. Let's say you have 2 SO3 gas giving you 2 SO2 gas plus O2 gas, and you're told to calculate for Kp. If your Kc is given as 4.08 times 10 raised to power minus 3, and your temperature is 1000 Kelvin. Yes, okay, this is something similar to what we just finished, so I believe we should have a way to solve for this. Remember, once again, our relationship is Kc RT delta n. And let's first solve for delta n. Delta n is equals to 2 plus 1, that is C plus D minus A plus B. But here we are left with just one reactant, that is 2. 2 plus 1 is 2. 2 minus, okay, let me write this way. We are just left with A, so we are working with this. 2 plus this, that is 3 minus 2, that is 1. Then our temperature is already given in Kelvin, so there's no conversion that we need. Our Kc is given as 4.08 times 10 raised to power minus 3. Simple, we just need to substitute. So we have Kp is equals to Kc RT delta n. So our Kc is given as 4.08 times 10 raised to power, times 10 raised to power minus 3, times 0.08206, yes, times 1000, all raised to power of what? 1. All raised to the power of 1. Then if we do this on our calculator, we should be having a simple answer of 0.3348. Yes, 0.3348, which is approximately 0.335. as our Kp. So this becomes our Kp for the reaction, and that is how we have shown the relationship between Kc and Kp. There are other questions that you may have where you would be given your Kp and you'll be told to find your Kc. All you just need to do is to make your Kc the subject of formula. So if I want to make this the subject of formula, if I were to look for Kc when I'm giving Kp, definitely my Kc will be Kp over RT delta N, right? So, and if I were looking for something that has to do with my temperature, because there are times when I have to do my temperature, the mistake people make sometimes is that this delta N is for your molar gas constant and your temperature. So if I were looking for T, definitely I know that this is going to be first I will be able to expand this. That will be Kp is equals to Kc, then R delta N, then T delta N. Do you understand that? So if I were looking for just my T, I know that I have to make T the subject of formula. That becomes T delta N is equals to Kp over Kc R delta N. And because this is a power, so definitely I have to find the root of this power to find my temperature. So temperature would be gotten one way or the other. All you just need to understand is how to manipulate and get your subject or formula. But please don't make the mistake of using another value for R. Most cases in this question, the value for R that is used is 0.08206 or approximately 0.0821. This is the value of R that is used, our molar gas constant. Thank you very much for watching. See you next time, and please, once again, don't forget, this is Further Solutions Academy. Further Solutions Academy. Please share and subscribe to our YouTube channel, and if you want to reach us on +234 80 344 95990. You can call us, you can reach us on WhatsApp, and you can also reach us on Telegram. Thanks for watching, and see you in our next video.